We are recording now.
Okay. Do you see the screen?
Yeah, we see the full desktop. Now, okay, now it's full screen.
Okay. Do you want me to start right away, or you want to introduce it, the talk?
Yeah, no, we did a presentation on the organization, so you can start right away.
Okay, so I will start then. Hello, everyone. I'm happy to be here and to present this training course. I don't know if we can call it this or just a rather long talk on the advances that we've made on non-hydrostatic simulations using CROCO. So this talk will be divided in two parts. One part is the explanations of the methods, the description of the methods. How do we make a non-hydrostatic model? And then I will show some simple applications and some applications that are less simple. And then I will finish with some thoughts about numerical aspects of the problem when doing non-hydrostatic simulations. So maybe to introduce this presentation, we can look at a spectrum of the different processes that we see in the ocean. So you see on top a spectrum that goes from the large scales to the mesoscale, sub-mesoscale, etc. And in general, with our regional coastal models, we tend to model the mesoscales and some of the sub-mesoscales with resolution that are about 1 kilometer or less, maybe a few hundred meters. And we hope that the parametrization that we use to model what is below the few hundred meters work fine. But in this area, there are a lot of processes that we don't understand very well. Internal waves that break into stratified turbulence. Then we have three-dimensional instabilities of all kinds and an inertial zone in which these instabilities go down in scale more and more until they get to the dissipation zone. We want to be able to model these processes and then to feed back the processes into the larger scales. And that's the reason why we are developing models that can do that. When we get into the region of the, let's say, 100-meter scale and below, we enter a region that we call non-hydrostatic, and I will explain a bit better what it means. And for that, we need to change the model a bit and to develop non-hydrostatic solver. When we go down to 1 meter scale, then we enter the zone of large eddy simulations. And we want to be able to do this kind of simulations too. When we are above this scale, we say that we do RANS simulations, Reynolds average Navier-Stokes equations, which is quite similar, but we don't fully resolve the large eddies that we will see in this presentation sometimes. So this is for the introduction. And now we are starting the part of the presentation that presents the non-hydrostatic solver. That is, how do we make a model non-hydrostatic? There are two kinds of methods that I present here, the main ones. The first one is the really classical method. It's called pressure correction. And it is made for incompressible equations. So most ocean models use this method. And the second one is a compressible approach. In this case, we release the assumption of compressibility. And this is something done generally in atmospheric models, which are, because the atmosphere is much more compressible. But we will see that it is very useful to use it in the ocean as well. But we are the first one to do it. That is, CROCO is the only model that is using this approach. And that's the one we are favoring right now. Okay. So I start with the pressure correction method. So as I said, it's for incompressible equations, incompressible flow. And all models trying to do that use this pressure correction method. For example, the MIT JCM is one of the best known among modelers. And for CROCO, some people in Brest and in Los Angeles have worked on a version of this pressure correction method that is not implemented yet on CROCO, but it will be soon. So I will describe how it works. And I think that not everybody will understand the details, what I will say, but well, I hope that you at least get the essence of the idea. And that will be enough for this class, I think. So the idea is to separate the pressure into three components. One is the atmospheric pressure that puts the boundary condition at the surface of the ocean. Then you have the hydrostatic pressure, and that's the one that is in equilibrium with gravity for the vertical part. And then you have Q, which is a non-hydrostatic pressure. We can then write below the homogeneous linearized equations for simplicity, so there are no advection terms here. And you see that there's a non-divergent equation. So we write the equation for U and W. So one component is horizontal and one is vertical. And then you have the momentum equations for U and W below that are written in terms of the non-hydrostatic pressure gradient. The problem here is that we don't have an equation for this Q value. So the technique is to write the momentum equation in terms of the provisional solution, that is the U tilde n plus 1 is a provisional solution computed from the hydrostatic equations. And then the non-hydrostatic solution should be equal to the hydrostatic solution in which we add the non-hydrostatic pressure correction. So if we take this equation, I don't have an arrow to point, but okay, that's the equation on the right top. If you take these equations and you use the non-divergence, then you arrive into the equation below, which is a diagnostic equation. It's not a prognostic equation anymore. And it is an elliptic equation. That is that the Laplacian of Q is equal to the divergence of the provisional values, provisional solution. This means that we broke the divergence, the non-divergence hypothesis when computing the hydrostatic solution. And we are going to correct this loss of assumption using the non-hydrostatic pressure. This is relatively consistent with the physics. That is, it's the compression that breaks the divergence, and the compression is sending acoustic waves to repair, if you want, to correct the loss of non-divergence. The problem here is that it is done immediately, as if acoustic waves were infinitely fast, and they will correct the divergence right away. So it is a global computation that is made. That is, all the points of the domain are calculated in the same procedure using a Poisson solver. And this can be a problem for parallelization. Another problem is that we don't use a simple 3D model. We use a model that is split in time between the barotropic part and the baroclinic part. So the barotropic part is the depth average flow. And it is integrated with a faster time step, the delta TF on the scheme on the right. And that can pose a problem that I will describe quickly. Trust me for the details. So we have to compute the barotropic components before we make the correction to remove the divergent part of the equations, as I said before. And when we do this correction, we realize that the depth average of the new solution that has been corrected is no longer equal to the barotropic part. And that is a source of instability, which is very difficult to correct, actually, and it's problematic. So there are few solutions that have been found, generally ad hoc. And one solution that was found for CROCO was simply to change the surface boundary condition. Instead of taking Q equals 0, we take dq dz equals 0. It's the importance of what is done here is that when you do this change of boundary condition, the surface becomes hydrostatic. And what it means is that we cannot solve short surface waves. So that's another problem of this method for, at least for split explicit time stepping. So if I summarize the problems with the pressure correction method, it is the inconsistency, potential inconsistency between the 2D and the 3D component, and that prevents resolution of short surface waves. And then there is the problem of the Poisson solver. First of all, there's a complexity in sigma coordinates with these solvers that are quite hard to circumvent. And then there are parallelization issues with global computations of this solver. And I will illustrate that a bit after. So that makes me come to the second approach that we use more often in CROCO nowadays, and that's the compressible approach. As I said, it's an approach that is common in atmospheric models, but not in ocean models, not at all. The reason why we do it, that could be a physical reason. As Dukowitz said, these acoustic waves are in general negligible, but their effects, or the effect of the approximations in the equations, may not be. He was thinking of acoustic radiative waves that could be important for the physical solution, but maybe not. But we can add to this the fact that the compressible approach may be simpler to implement and with numerical and computational advantages. So I will try to illustrate this very quickly also. So I take the same equations as before, but instead of using non-hydrostatic pressure, I convert this non-hydrostatic pressure into something that is proportional to compressible density. Here CS is the sound, the speed of sound, and CS squared times delta rho is the non-hydrostatic pressure. You introduce that in the equations, and you get, instead of non-divergent equation, you now have an equation for delta rho, which describes the compressibility. And that means that we can solve these equations with the non-hydrostatic terms at a fast step, at the same time step as the barotropic mode. And all the computations now are local. You don't need a solver, global solver, to resolve the non-hydrostatic pressure. The divergent part is corrected as it should in the real world by propagating acoustic waves, and that's how you compute the non-hydrostatic pressure and the correction that is made to the flow. So the advantages of this approach, one is for the physics. You can solve short surface waves in this case, because there are no approximation for surface conditions. You can also solve mixed acoustic rarity waves, which can be generated by tsunami, for example. So it can be interesting for tsunami precursors. Then numerically, it is interesting because we can use a higher order pressure gradient. And we are not limited to the second order as for the solver, the Poisson solver problem. Therefore, the accuracy for internal waves can be improved. And then in terms of performances, of course, we think that solving acoustic waves might be detrimental to the performances, but this is not so drastic because of a few steps that have been taken. One is that we can reduce the sound of speed without affecting the solution, at least the non-hydrostatic solution. So all we need to do is to have the sound of speed larger than the barotropic phase speed, maybe 5 times, maybe less, but about this order. But doesn't need to be 1500 meters per second as it is in the real world. Then another step is to use a semi-implicit treatment in order to reduce the burden on the time stepping. And then we account for the good scalability for parallelization. And this is a very good advantage if you use massive parallelization for very large problems. And this slide is here to illustrate the aspect of parallelization and scalability. We analyze that in terms of speed up, which is the computational time required to integrate a solution. Here, it is a solution of a sloshing wave, which I will present a bit after. So the time to compute this solution with n processor divided by the time to compute the same solution with twice as much processors. If the parallelization is optimal, you should have a speed up of 2. And if it's super optimal, you can have a bit more actually. This is due to the fact that you have an optimal use of cache memory in the computer, but I will not talk about this. So here in the plot, we compared the speed up for the NBQ approach, which is the compressible approach in red, and below the non-hydrostatic approach with the pressure correction method. And you quickly see that the compressible approach gives a speed up of 2 for every kind of subdivision of your domain, while the pressure correction method is not as successful in this sense, and the speed up can be as low as 1, and it's rarely approaches 2. So of course it depends on the solver, And for CROCO, they have tried new kind of solvers that are a bit more efficient, but you can never reach the efficiency that is given by a local computation. So here I finished the presentation of the method, and I will show some applications. First of all, I will show simple applications that are part of the test cases in CROCO. Okay. So I will start with wave propagation problems. Okay. All right. The first case is the tank. It's a sloshing wave case that I talked about before. So the tank is being tilted, and we generate a standing wave that is the addition of a propagation in one direction and the other. And here I show the domain that is being used. It is 10 meters by 10 meters, so it can be considered as deep in terms of waves. And the resolution is 20 centimeters. The first application or simulation is done in the hydrostatic case. So for this case, we have an analytical solution, which is given below. So it has a dispersion relation that is independent of the wave number, so it's non-dispersive. The waves are non-dispersive. And then there's this analytical solution given here for the free surface U and W. And you can see that the solution is matching exactly the analytical solution. So the numerical solution in red is matching the analytical solution is black. Actually, you can't even see the black line because it's hidden behind the red. So we just verified that the hydrostatic model works, but we knew that, but it's always good to check. And then we have the non-hydrostatic case, and this case helped us a lot to develop the method because it is very sensitive to any bugs that you can put in the model. And you can see that in this case, we also have an analytical solution. In this case, the solution is dispersive because the dispersion relation shows a dependence on K. But the model reproduces the analytical solution for this non-hydrostatic waves. And again, the match is very good in terms of phase error and amplitude error. The errors are very small, even for a long time after the initial stage. It means that the errors in dispersion and diffusion is relatively small in this case. You can try to change the acoustic wave phase speed, and you'll see that you can have changes in the value of the error in this case. So you can test the sensitivity. You can do that later with Andres, and that will be interesting. As you can see, the period of the waves here is much slower than the hydrostatic case, which I show again. There was 2 seconds before, and now 3.6 seconds. So the waves are a bit slower. Okay, the next test case is the internal soliton. It is also part of the basic CROCO test cases. It is also based on a tank that is being tilted, but in this case, it's we're not interested in the surface, in the free surface, but we're interested in the interface between two layers of fluid, one that is heavy, and above it we have a light fluid. Maybe that could be representative of an estuary with fresh water on top of heavy water. And this interface is being tilted at the beginning, and it generates the propagation of a wave that will tend to form a bore and then a train of soliton when some waves detaches from the front. Here we don't have analytical solutions, but we have a tank experiment that we can compare to, even if it's not exactly, the experiment is never done exactly in the same way as the numerical simulation. But you see again at the beginning the bore that is being formed, and then at some point the train of soliton that is detaching from its bore. And what we have besides the laboratory experiment is the equation of Korteweg debris, that is the KdV equation that maybe some of you know. The KdV equation expresses two things. So there's a propagation, and the propagation is altered by two terms. One is a nonlinear term, and one is a dispersion, a dispersive term. Dispersion is generally given by a third order derivative, or any higher order derivatives that are of higher order than this. So here a third order derivative translates into a dispersion of waves, that is waves that travel with different speed according to their wavelengths. And this term here is the nonlinear term that is producing steepening. That is, it does the opposite of dispersion. It tends to keep the wave packet together. So you have a balance in this simple equation between a process that keeps the wave together and a process that tends to disperse the waves. And that's the reason why the soliton can travel a long distance without being altered too much. And we can resolve this KdV equation numerically, and generally it shows very good results with the numerical model. Okay, I have talked about waves and the test cases that validate the simulation of waves in CROCO. I will start now talking about eddies, and particularly large eddies, that is, eddies that are three-dimensional. So this diagram is a bit similar to the one I showed at the beginning. It shows the resolution of eddies across the scales from large-scale eddies to the dissipating eddies. So if you have a resolution that is very high in the range of the dissipation, then your model is a DNS model, direct numerical simulation. You resolve everything. If you resolve only the large-scale eddies and you let the rest go, you are in LES modeling. In this case, the large injection of energy is resolved by the model. All the big 3D instabilities that inject a lot of energy is resolved. And in the inertial part of the spectrum, the eddies only decay in scale progressively until they are dissipated. If you don't resolve completely these large eddies, then you are doing a run simulation. And often we tend to mix LES and RANS, and we don't know exactly where we are. But that's something that needs to be resolved by trying and using different kinds of closure models. We'll talk about it towards the end. Here, I will just illustrate what it is to resolve three-dimensional eddies by a few test cases that are also included in, some are included in CROCO and some are not. So this one, the Kelvin-Helmholtz instability, is included into CROCO. It is a very classical type of 3D instability. It is very well known. It has been studied in particular in the case of CROCO by a group of people in Toulouse. And the publication is Penne et al. 2018, so it's relatively recent publication. And the instability condition is the one that are written here. It's given by the Richardson number, which is the ratio between buoyancy and shear. So if you have some shear, you will tend to generate a shear instability. If the flow is homogeneous, there is no restriction to this shear instability, unless there is too much damping. But if you have a stratification that gives buoyancy, then you will tend to control the shear instability. And if the buoyancy is too strong and Richardson number is high, then you have no instability. And if the Richardson number is below 0.25, you will get an instability. So it's a relatively simple protocol to follow. And there are still a lot of people actually that are trying to study the Kelvin-Helmholtz stability as a fundamental process. In particular, the way they mix the layers of fluids. Here I will show just a quick animation that is from Penne, and it shows the destabilization of the Kelvin-Helmholtz, the fluids in the Kelvin-Helmholtz instability. I can play it again. And you see the roll up, and then you see also merging of eddies that grow in scale. So this is obviously a two-dimensional simulation because you have an inverse cascade and a growing scale, but we can also do a three-dimensional simulation, and in this case the flux of energy across the scale is different. And these simulations were used for diagnosing the mixing of the two waters, the two type of waters. Another way to produce Kelvin-Helmholtz instabilities is using the log exchange experiment. It's very similar to what we've seen before with the tank, except that this time you have the heavy fluid to the left and the light fluid to the right, and at the beginning they are separated by a wall. And you release the wall instantaneously, and you let the fluid equilibrate, adjust, and there is gravitational adjustment that then produce a propagation in one direction and the other until the fluid becomes equilibrated with the light water on top and the heavy water at the bottom. We have some kind of analytical solution for that, but not for the instability, just for the wave propagation. And we know that the wave propagation is dependent, depending on the reduced gravity, that is on the difference of density between the two fluids. And of course, the instability will be also to some extent. We have some tank experiments that can be compared to this kind of simulations also. But the instabilities chaotic and don't match exactly your solution, of course. It's just statistical matching. In any case, this test case is in CROCO as well and can be used. It can be used in hydrostatic case and non-hydrostatic case. In the hydrostatic case, of course, you don't produce this kind of instabilities, and the line remains very flat until equilibration. Okay, other type of instabilities and test cases can be done in CROCO. They are not part of the distributed cases, that the basic cases that we distribute with the model, but they have been produced with CROCO. One is the Ekman layer problem, which can be compared to other LES models. So you produce an Ekman layer by resolving the instability, which is a shear instability, a vertical shear instability. And in this case, you have, of course, a Coriolis force. Therefore, the currents that are generated tend to rotate with depth. And we could show that CROCO could reproduce the Ekman layer very well. Another kind of problem was the case of a sub-mesoscale vortex that would be unstable to inertial or symmetric instabilities. And this is something that is being done at the moment, that has just been initiated, but it seems to give some very interesting results also. And another case of illustration that I show on the right is an hydrothermal plume that is the problem of convection in this case. So you have a source of light water at the bottom, which could be an hydrothermal plume, of course, and the light water will rise in the column due to convection and rise to the point where there's a balance with buoyancy. Okay. This is another application that has been made by a team in Poland. In this case, we use wave average equations of CROCO. In particular, the term that is given by the interaction between the currents and the stock drift coming from the waves. This term is called the vortex force, and this is the term responsible for Langmuir circulation. The Langmuir circulations are very common in the ocean, as you may know. They tend to produce strong convergence at the surface. So these are lines of convergence that are separated by a distance of about 100 meters. You see an example of this in the bottom here, where sargassum has been trapped in this line of convergence. So they show it relatively well, and some people are studying the effect of Langmuir circulation on this trapping effect. And another application that can be made and was made by this group in Poland was for fragile ice, which is a melted form of ice in the polar regions that tends to be trapped also in these Langmuir circulations, as some images have shown. And here what I show is a picture of the model. It is the velocity, I think, of the model. No, it's the fragile ice concentration, I think. It has been done with a resolution of 3 meters. And it shows also the parallel lines of the Langmuir circulations. Well, it has been analyzed in details by these authors. Okay, so I have come to the end of the simple test cases, I would say, which we are treating the fundamental 3D instabilities. And I will now address some problems that are a bit more complex, that are using the fundamental processes, but within a more realistic configuration. One of them is the case of nonlinear internal waves at Gibraltar, and I will go very quickly on that one because it will be presented after by Laurent Rogout. And then I will present another case which I work about at the moment. It's the case of surface waves. So first, nonlinear waves. This is a simulation that was done by Lucie Bordois a few years ago already, and that shows the propagation of very large soliton generated right at the Strait of Gibraltar and entering the Mediterranean Sea. And this is the kind of dynamics that we want to catch with the model within a realistic simulation. Here at the bottom, you see the comparison with the KdV equation again, the one that I mentioned before. And you can see that we reproduce with the model the KdV dynamics pretty well. In blue, you see the hydrostatic solution, which is really not performing well for the generation of the soliton. So this is typically a non-hydrostatic dynamics. Small internal waves can be hydrostatic, but large internal waves have non-hydrostatic component that is quite strong, and it generates soliton. This is another animation that I show quickly. It is at a higher resolution that the previous one. This is the beginning of the simulation where there is a build-up of the front due to the tides, and you see also some Kelvin-Helmholtz instabilities here on the left side. But when the tides will reverse, then we will generate a strong internal wave. This is a two-dimensional model with one horizontal and one vertical dimension, but a three-dimensional model is also being run by Margot Hilt, who is presenting her PhD very soon. So here you see the internal wave with the trend of soliton generated and dispersing. Okay, but Laurent will talk more about this, and he will talk also about the nesting approach that we can use for realistic applications. I wanted to mention this because nesting is the way that we can bridge scales, because we are talking about very small scales, very fine processes, but we want to do that also connected with the large scales. So we need to bridge gaps that are very large between the kilometer scale, for example, and the meter scale or the tenths of meter that we want to use for resolving the processes. So nesting is one way to do it, and we are now developing a multi-grid approach in which we can nest more easily and more automatically the different parts of the grid. Then Laurent will talk more about this. Andres, could you tell me if we have a break? We're having a break or not?
Yes, let's stop for 10 minutes.
Yeah, we could stop here. It will be a good time. So should we stop for 10 minutes then?
Okay, I will stop the recording and then we'll be back at the hour.